All right, hi. Sorry for the delay. I don't know how I'm going to follow that, but I'm going to try. I'm going to try by starting with an example. And this is a very simple little program. I think everybody here probably understands what it means. I claim that it has two semantics, a strict semantics and a lazy semantics. So let's just walk through that to be sure. In the strict semantics, I'm going to start from left to right and just substitute through, evaluating as I go. So the first thing I do is I take x gets 3, I evaluate it, and I substitute 3 for x throughout. And I get this yellow program here, which just returns 3 after assigning error to y. Doing the same thing again, I evaluate y gets error, and everything blows up because there's an exception, and an exception gets thrown. On the other hand, I can think of this lazily as well. In this case, I start by looking at the return, and I ask, what do I need to evaluate in order for the return to return a value? And the answer is x. So I do the same first step I did the first time, substituting along x to get this program, y gets error, return 3, just as before. But this time, I look again at the return, and I see that it's already going to return a value. I don't need to do anything else. I can simply drop the rest of the program and get return 3. So this does seem to conform, at least somewhat, to our intuitions about strictness versus laziness. But what is causing this? Well, I want to think about this program as a program with two effects. The first effect is that it throws exceptions. This is relatively easy to see. Almost everybody recognizes this as an easy-to-see effect. On the other hand, the other one is a little bit more subtle. So I want to turn to how we think about effects. And we think about effects in opposition to how we think about types. Types describe how a program can combine. So if I think about programs like building blocks, I can think of types as the pips on the top and bottom of the building block that tells me how I can stick this block to other blocks. Alternatively, I can think about having an input, which is a natural number, as part of the type of some program. On the other hand, I think of effects as internal properties of programs. So in other words, in the building block example, it might be the fact that this building block is green. It doesn't change how I can combine it with other blocks, but it certainly changes the properties my entire structure is going to have at the end. On the other hand, we might have an effect like you don't use your input y. And that's exactly what we have here. This y input is actually never used in the rest of the program. So let's take this program apart and examine it a little bit closer to understand even more detail what's going on. In the y gets error part of the program, this clearly is effectful. It throws an exception. We're done. On the other hand, this return program never uses y. And recall that y is assigned to just before the return part of the program, so it's available for the return program to think about. It's in its type context. So we can think of that as an input to the return program. And so this return program might not consume its inputs. And we can generalize this idea a little bit and say that actually it can choose how many times it consumes its inputs, as opposed to being forced to consume it exactly once. Along those same lines, we can think of throwing an exception as this program might not produce its outputs. And we can generalize in the same way. This program can choose how many times it produces its outputs, rather than being forced to produce it exactly once. We call these producer choice and consumer choice of quantity. And it's worth thinking about, with these two effects in mind, what is pure programs? And it turns out that pure programs are actually linear, which is maybe a little bit unusual, but these are the programs that do not have either of these effects. So we can think of what's going on here, what's causing the strictness and laziness, as a race between producer choice and consumer choice for attention during program composition. If the producer choice wins the race, then when there's a problem, that is, when an exception is thrown, we don't have an input to feed into the next program. So we stop everything and don't produce any outputs at all. On the other hand, if consumer choice wins the race, then we don't bother to even check to see if inputs we don't need are ever produced. So we get a lazy semantics for the program. So in other words, we have strictness and laziness, which we can think of as something to solve, a problem in need of a solution. And we know we have a toolbox of effects that we've now argued intuitively can help us understand strictness and laziness. And it turns out that there are some tools in the toolbox that are very useful. The most famous, of course, is the tool of monads. Everybody knows that we love monads when thinking about effects, but it turns out there's another tool that's really useful as well, and that's the opposite, comonads. And we want to think about how we can use monads and comonads to explain strictness and laziness. And once we do that, we're actually helping to answer a question that shows up when thinking about the semantics of effectful programs, which is how do we use monads and comonads together to talk about effectful programs? So our strategy is going to be take an effectful language and embed it into a pure language, where we have to make our effects explicit so that we can see how they interact. Now, recall that I said that in our case, pure programs are linear. So we're going to take a nonlinear language with exceptions. We're going to embed it in a linear language. And linear languages don't ever have exceptions, because then they wouldn't be linear anymore. So we create one of each of these in the paper. We say comp, which is just a language of computations. It's a language with strict and lazy semantics. It's incredibly simple. And we have proc, which is a language of processes. It's a language of processes because its type system is a model of linear logic. And processes are a known good way to have a type system model of linear logic. So let's think about how we can embed some of these programs, these effectful programs, in our pure language. With exceptions, this is very well known. We simply modify the program into a linear program that now returns a result, but that result is maybe. And maybe, as I'm sure all of you know, is either some value, representing a successful run of the program, or nothing, representing the fact that an exception was thrown. And this is well known to be a monad. And what monads bias is they bias the ability to compose. So if I have another program which can throw exceptions, I can translate it to another linear program with this maybe type in the output, but now I have a type mismatch between the yellow maybe sigma and the green sigma. But monads give me the ability to, an operation called bind on programs, and bind lets me find a program, maybe sigma to maybe rho, and now I can do my composition just fine. And the way this composition works operationally is if this yellow program throws an exception, then we're going to propagate that exception forward so that the whole composed program throws an exception, and notably, the upper green program here never actually runs. On the other hand, we can also look at capturing programs that can drop their inputs. And we do this using a comonad. And we write that comonad as bang. And this bang comes from linear logic. It's well known to be a comonad. I'm afraid I can't go too much into the details of logic here. Please look at the paper. We go quite deep into them. But again, comonads bias the ability to compose. So if we have another program and we bring it into our linear world, we now have a bang sigma on the green program and a sigma on the yellow program. But comonads give us the opposite operation to bind, called cobind, which lets us move this bang to the yellow sigma, allowing us to compose. And operationally, the way this works is that if this green program drops its input, then cobind propagates that drop backwards, dropping the input of the yellow program, and the upper yellow program never needs to run. So, in other words, when embedding comp in proc, we take programs that have exceptions and we embed them into monadic programs. And here I've written the question mark monad. This is a generalization of the maybe monad. It comes also from linear logic. We embed programs that drop their inputs as comonadic programs that use this bang comonad. But it's not as clear what we should do with programs that can both throw exceptions and drop their inputs. And this is exactly the problem, how we use monads and comonads together. Now, the straightforward thing to do, that we would very much like to do, is bang tau to question mark sigma. I can drop my inputs, and I can throw exceptions. And if I think about just composing effectful programs, it should be that the composition of a program that can throw exceptions and drop its inputs should be able to itself throw exceptions and drop their inputs. But if I think instead of embedding these into the linear world, I get this type mismatch again, this time between a question mark sigma and a bang sigma. And I can pull the same trick I did before, using a bind on the green program and a co-bind on the yellow program, but the type mismatch remains this time. There's the bang question mark sigma and a question mark bang sigma. And the traditional solution when dealing with monads and comonads in this case is to say, let's find something called a distributive law. And a distributive law lets me just move this bang over this question mark and everything's golden. And indeed, this does work as a model of these composed programs, except this is a traditional solution to this problem of how we use monads and comonads together, but there's a problem, and that's that in this case with bang and question mark, there's no such thing. Can't do it. So we can't use the traditional solution. So what do? Well, we go back to our analogy earlier of a race between consumer choice and producer choice. And instead of just saying one of the two of them is going to win at each composition point, we're going to pick a winner. Let's start by picking producer choice. And we pick producer choice to win using what we call the monad prioritizing layering. And this embeds programs from comp into proc using this formulation, bang to question mark bang. And the neat thing about this is that while there's still a type mismatch here, it can be resolved simply by using bind. And now we can compose just as normal. And we know how bind works operationally. If this yellow program throws an exception, then bind propagates that exception forward so that the top green program never needs to run. Again, a strict interpretation of the program. So we can embed programs that throw exceptions and drop their inputs using the monad prioritizing layering. That's one choice. On the other hand, we can flip who we choose wins. And to do that, we, perhaps unsurprisingly, use the comonad prioritizing layering. And the comonad prioritizing layering looks kind of the opposite of what we had before, where now you have bang question mark tau to question mark sigma. And again, we can simply resolve the type mismatch we still see here, this time using the cobind of our comonad. And we can compose normally. If we do so, we know how the cobind works operationally. If this program drops its input, this green program, then we propagate that drop backwards so that the top yellow program never needs to run. Again, the lazy semantics of the program. So we can use the comonad prioritizing layering here as well. That's another valid choice. So we actually do prove that this works for our example languages. So if you take a comp program from tau to sigma, and you evaluate it strictly to a value, or you layer it with the monad prioritizing layering, embedding it into our linear language, you can evaluate that proc program to a value. Note that this is linear, so there is no strictness and laziness to worry about. Everything works out the same. Embedding this with the monad prioritizing layering, I've written kind of suggestively here, does indeed get you the same result. And from the point of view of lazy programs, the same thing holds, evaluating a program lazily or embedding it using the comonad prioritizing layering. After evaluating this proc program, does indeed give you the same result. So somehow, the answer to the question, how do we use comonads and monads together, from the point of view of layering, is you have to pick a layering. And this allows us to look at the problem of strictness and laziness now through the lens of effects and understand them differently than we've understood them before. But it turns out that that's not all we can do. We can generalize this notion. So we can think about a program with some arbitrary producer effect. That is a monadic effect. And we can think about its monad prioritizing layering, and this will give a strict semantics to the effect, and in the sense that it will run even if that program is never needed in later composition. On the other hand, the comonadic prioritizing layering will give a lazy semantics in the sense that it won't run the effect if that effect is never needed. And we can in fact generalize further to arbitrary producer effects and consumer effects. And we get a monad prioritizing layering, which is strict, and a comonad prioritizing layering, which is lazy. But it's worth noting that with arbitrary monads and comonads, all sorts of crazy behavior can occur. It might not look like strict and lazy from the outside. So in this case, where you have an arbitrary monad and arbitrary comonad, you might or might not have a distributive law. And if you don't, you have two choices. You can use the monad prioritizing layering or the comonad prioritizing layering, which is a choice between strictness and laziness in some sense for your effects. On the other hand, there might be a distributive law. And if there is, you can choose the monad or comonad prioritizing layerings, but you can also use the distributive law-based semantics that everybody saw earlier. Luckily, we have a theorem about how these connect, and that's that they're all the same. But notably, this only works when there's a distributive law. And an interesting corollary appears here. We saw earlier that our example program had strict and lazy semantics, and that these comes from the monad and comonad prioritizing layerings. And this tells us something we had only been able to assert before, which is that there is no distributive law of bang over question mark. If there was, strict and lazy would be the same. So I really recommend that you guys look at the paper. There we actually go much deeper into several things, including connections to logic. We look at both classical logic and linear logic. We formalize doubly effectful languages, languages with both a producer effect and consumer effect, and give a categorical formulation of all of this. There's theorem details in there as well, although more of them are, of course, in the technical report. So thank you very much.
Thank you. We've got a number of questions for you. Why don't raising exceptions and dropping inputs have a distributive law?
Because strictness and laziness are different. They just don't. It's relatively easy to prove in linear logic.
Okay, sort of maybe a related question. You've made a case that dropping a variable is an effect. Why is using one twice an effect?
So it's harder to see in this case. But if you look at other effects that you might have, other monadic effects. So if you think about probability spaces as your monad, using a variable twice is the same as, well, you get a choice between do you split this probability space apart, flipping your coin twice, or do you flip a coin and then use the thing twice? So you get the same sort of difference.
Okay. Does laziness here mean call by name or call by need?
In the paper, we use call by need. In other interesting cases, such as the probabilistic case I was just talking about, which I've been thinking about quite a bit recently, you really want to look at call by name, so.
How does your approach compare with the standard approach of using polarized types to indicate strictness or laziness and mix the two?
Yeah, it's just a very different point of view in some ways. This is really talking about whole program, or whole language even, because we're embedding into one language into another. But I think also just we don't talk about types much at all, other than as a way of reflecting the effects. We think about all of this from the point of view of effects.
Mm-hmm. Another question here. Monad transformers have their priority determined by the layering. How does this relate to your layering?
I'm not sure. I haven't thought about that.
Okay, can think about that. What if I have multiple monads or multiple comonads? Is there a way to layer those?
Yeah, I've been actually thinking about this recently. In particular, looking at something like the graded monads that we saw in the last talk, and how we can expand to there. I have some notes on that. I'm still working on that.
And another question on layering. Would it be possible to have a language where you can choose the layering at each composition point, or do you have to remain consistent throughout a program?
Yeah, I mean, arguably that might be in some hidden way what the polarization stuff is doing. I'm not really sure.
Mm-hmm. And another composition question. How well do program fragments interpreted with each of the semantics fit together? Can lazy and strict programs compose together well?
Yeah, it's not really. Not from this point of view. Perhaps with a more nuanced version of this it would, but that has yet to be developed.
And then there's a question here about sequent calculus, where an analogous problem arises when reducing stack abstraction against a value abstraction with an analogous solution. So you favor one or the other, either the values or the stack, yielding call by name or call by value. Is there a relation between that and what you're doing?
Absolutely. So it turns out that the monad prioritizing layering and comonad prioritizing layering actually sort of originate from the sequent calculus world, where you look at embedding classical logic into linear logic using the banging question mark exponentials.
Okay, and one final question. Could you give some examples besides error, maybe, of how using monadic and comonadic tools together help us write better programs? And better to me means faster, less errors, or faster development. Yeah,
I mean, so this is a really interesting question with a lot of areas of development. I know there are some work on, well, I'm working on right now some work on looking at probabilistic programming through this point of view and using this to develop new ways of reasoning about probabilistic programs. But this paper is really focusing on just thinking about things from this strict and lazy point of view.
Okay, thank you very much.